All right, so I think this is recording. Let's take a look at this quadratic inequality. We always want to make sure that we're comparing it against 0, and we are. We want to look to see if there's a greatest common factor among the terms. There's not. And now we want to factor this. Since the leading coefficient is different than 1, it's suggested to use the x method. It's something that you learned in Algebra 1 and you used it in Algebra 2. And there may have even been situations where you used it in geometry to solve some of those problems. So you've definitely seen this before, or at least you should have. So now the trial and error portion, we want to try to find two expressions that when multiplied together give us the top of the x, but when added give us the bottom of the x. And so that's pretty easy in this case because negative 4x times a positive 1x will give us the top expression, but when you add these together you get the bottom expression. Now, we can't come in and use the negative 4 and 1 to come over and factor. What we have to do is use a table down here to get the factors. So we return to our original equation and use the first and the last. That's how we got the top of this x, and that's how the numbers that we put in the diagonal of our box down here. So we've got 2x squared minus 2. And now the values that we found in our x go along the other diagonal. It doesn't matter whether I put the negative 4x here or if I put it here. So now we factor both horizontally and vertically. If we look horizontally here, if we look across, negative 2 divides both of those. The greatest common factor of those two terms is negative 2. And these two are, they call it prime with respect to each other, so we just put a 1, and x times 1 is x, and x times 2x is 2x squared. So there we have it, our factors. We've got 2x plus 1 times x minus 2. So the reason we want to see that in factored form is we're going to find what they sometimes refer to as critical points, and they're going to divide our number line into 3 regions, and within each region we look to see whether or not it's in the solution set. So if we set 2x plus 1 equal to 0, you can see that negative 1/2 is the solution at, because this is a 2-step equation. Subtract 1 and then divide by 2, and you have your answer. And you can see this other factor is just a 1-step equation. If x minus 2 equals 0, then x has to be 2, but 2 minus 2 is 0. Pretty easy to see. So that divides our number line into 3 regions. We could call them anything that we want. I just typically call them A, B, and C. Now, I have a decision to make right away of to shade or not to shade these critical points, and that's determined for me when I look at the inequality. Since it's a greater than or equal to, since it has this equal to portion, I'm going to include them in the solution set. I know that if I take these two numbers, either one of them, and substitute it in for x, the resulting arithmetic is going to be greater than or equal to 0. All right, so let's proceed in a table, and it's just an organized way for us to find our solution set. So I'm going to give titles to my columns in my table, a test point, then I'm just going to write the inequality, and I'm going to use it in factored form. I guess the original inequality would be fine, but it's easier for me oftentimes to plug in my test point into the factored form to check to see whether this inequality, whether the resulting inequality is a true statement or a false statement. So over here, I'm going to record the truth of that statement. So let's take a look at region A and pick a point that's at region A. I want to pick a real number that is smaller than negative 1/2. So I'm going to pick negative 1. Negative 1 is to the left of negative 1/2. If I replace x with negative 1, what do I have? Well, positive 2 times a negative 1 is negative 2, and negative 2 plus 1 is a negative 1. X minus 2 is now negative 1 minus 2, which is negative 3. And that's a true statement because the negative times the negative is positive, and 3 is greater than or equal to 0. So that's true. And I'm going to include every point in region A in my solution set. In B, I'm going to pick a test point. And since I see that I've gone from negative numbers to positive numbers, I know 0 is in this interval. And 0 is easy to do arithmetic on, and it's a nice test point to pick. When I replace x with 0, I get 1, negative 2 for that factor. And it's a false statement. Negative 2 is not greater than or equal to 0. So it's not shaded on my number line. Kind of run out of room. So I'm going to try and shrink this up a little bit. Give us some more room. Even with all the years of using these software, it still amazes me that I can shrink this up and how nice and easy. Well, I don't know why I didn't grab that. Oh, it must be in a different layer. All right, so let's extend our table. And let's look to region C, and a number that's bigger than 2, well, I would just pick 3. So 2 times 3 is 6, and 6 plus 1 is 7. 3 minus 2 is 1. 7 times 1 is 7, and 7 is greater than or equal to 0. That's a true statement. So that's in my solution set. So I'm going to shade that region. So I'm going to shade here in region A, and I'm going to shade here in region B. So if you're in either one of these two sets, if you're in this one or if you're in this one, any points in those regions will be in the solution set. They'll make the original statement a true statement. Pick something that's not in our solution set and plug it in, and it'll result in a false statement. All right, so let's describe this picture using inequalities. If you're to the left of all those points are to the left of negative 1/2, that means that x is less than or equal to negative 1/2. I include the equal to because we shaded in, that's a solid point. So you're in this interval, or you're in this other interval where x is greater than or equal to 2. So there's our solution set written in inequality notation. All right, I hope that helps, and I will talk to you later. Bye.